Okay. I won't introduce my name again, but I will emphasize I'm a master's student from the Department of Mechanical and Mechatronic Engineering from Stellenbosch University. And in this paper, I will go over architecture that will be used to apply the concepts from the previous presentation in a practical use case environment. Okay, so an overview of this presentation, I'll give a very, very brief background just to remind ourselves, and then discuss the objectives of my research and go into the architecture with an illustrative example, and then conclude the presentation. So as mentioned, the IoT devices, they lack in standards, and we are looking to develop an architecture that supports and embraces the heterogeneity of IoT devices. So our research group has widely used digital twins, and has explored their use cases for large complex systems. As shown is the service-oriented architecture for digital twins, which I will not go into in great detail. But I do want to emphasize that this architecture supports the reflection of reality of heterogeneous data sources, and then also supports different types of digital twins. So digital twin instances, digital twin aggregates, and then this concept of a type digital twin aggregate. So to maybe refresh our memories from yesterday, which my colleague Reno had mentioned, the type digital twin aggregate is used to represent digital twin instances of a similar type. So you do not have to run unique digital twin instances. You can use a type to group these similar digital twins. The objective of my research is to develop a digital twin architecture for the provisioning, management, and monitoring of these heterogeneous IoT devices that improves the visibility of an individual IoT device's health and status using the available contextual information, and then also uses the contextual awareness and autonomy in the self-management of the device's state, and also promotes the scalability of integrating new and heterogeneous IoT devices into this architecture by loosely coupling the digital twins representation from other digital twins and available services. The architecture's context that we're working in, so there are various different stakeholders. Just get my pointer ready. There are various different stakeholders that interact with this IoT device management platform, and the IoT device management platform interacts with different types of IoT devices. So as mentioned, the different types of IoT devices, we're thinking of tens of thousands of IoT devices, and each of them will have various different types of use cases, and that heterogeneity is what we're aiming to support. And each device will have an application installed on the device to support a stakeholder's use case. And these applications or interact with an externally maintained backend, similar to the apps on your smartphone. Taking a bit of a deeper look into the architecture, I will not go into great detail in this presentation, but everything is in the paper. But this architecture is an adaptation of the service-oriented architecture for digital twins, and it makes provision for an organization's security requirements and the integration of heterogeneous IoT devices and managing the IoT devices across the various lifecycle stages. The services that are grouped, well, there are groups of services within this architecture. So there's platform management services, which are just used to maintain the platform's uptime. And then there are the DT management services, which are used to just manage the different digital twins within the system. And then lastly, there's the device management services, which are used to ensure the interaction with the different devices. Lastly, there is the service network, which just contains a collection of loosely coupled services that a digital twin may interact with. I've outlined a notification service, but this can be adapted to your particular use case requirements. I want to take a bit of a deeper look into the IoT gateway and the transformer, as these components will be adapted depending on the heterogeneous IoT device that you introduce. So taking a look into the IoT gateway, this is the the network entry point for the IoT device technology into the system. So we have the IoT device interacting with a communication mediator, and this in a practical sense would be your MQTT broker or your gRPC proxy of some sorts. And in the IoT gateway is a gateway configurator, which can dynamically add or remove IoT devices from the respective gateway. And there's an IoT gateway manager, which is the central manager of all the different types of IoT gateways to ensure that, well, manage all the different types of IoT devices within the platform. And then lastly, there's a credential mapper, which supports the mapping of the digital twins reference to the IoT specific reference as well. Taking a bit of a look into the transformer, this is a bidirectional translator of the data structure that transforms the IoT's data structure into the IoT device's data structure into a digital twin standardized structure, vice versa. And as mentioned, this interacts with a device credential mapper, ensuring that the appropriate digital twin or IoT device, well, a message is sent to the appropriate digital twin or IoT device. And then looking at an example of the digital twin's internal architecture, I've chosen the digital twin type aggregate. We can see how the digital twin interacts with various services. So I won't, again, go into detail on how this would all work, but it's all in the paper, or if you want to chat afterwards. But if we look at the provisioning process, the digital twin is orchestrating the interaction with the various required services. And there's a provisioning model which can be adapted depending on a provisioning process of a particular IoT device. Taking a look at the app installation service, the digital twin is interacting with the App Store and the device metadata, ensuring that it is compatible with the device, the app is compatible with the device, and will facilitate the installation of the app onto the device. And then taking a look at the monitoring process, the digital twin is interacting with the model. This could be a rule-based model or a machine learning model, and will infer the state of the IoT device with reference to the metrics and logs associated with the IoT device. And then if the digital twin detects that the device is operating within abnormal conditions, it can then send an alert to the notification service, alerting a user or performing whatever use case logic you'd like to introduce. So I want to just briefly touch on a bit of an illustrative example of how this would be deployed in your environment. So I've chosen a use case where there's a gRPC device that supports zero-touch provisioning, and then there's an MQTT-based device that supports zero-touch provisioning as well, and then an MQTT-based device that supports a different type of provisioning process. So we are supporting two different types of communication protocols, and then two different types of provisioning protocols. And then when we have a bit of a look into how it would be deployed, it looks a bit scary, but if we just follow the architecture from the previous slide, we can see that there's a transformer for different phases of the IoT device's life cycle that must adhere to security requirements. And then there's IoT gateways that are used for different phases of the IoT device's life cycle as well. And when performing tests for batch provisioning, so I want to emphasize what batch provisioning is. It's creating and then having a batch of devices request provisioning all at the same time. And I've conducted this test 30 times and taken the average for batches of 1, 10, 50, and 100 devices. And then I measured the time from the start of the provisioning process up until the last device was completed the provisioning process. And as shown is the times below. So we can see that for 100 devices, it took 8 minutes to provision all 100 devices. And this equates to about just under 5 seconds per device on average. Whereas for 50 devices, it took about 1.6 minutes, which equates to just under 2 seconds per device. So Scalability, well, yeah, it supports batch provisioning relatively nicely. So to conclude this presentation and the previous one, I want to emphasize that the management of heterogeneous IoT devices is a very, very complex task. But we have overcome a lot of those complexities and opened up a lot of future opportunities for such a platform using the digital twin design patterns. And in doing this, the digital twin can orchestrate the provisioning of the devices, well, orchestrate the management of the device's lifecycle, and also autonomously manage the device through its various lifecycle phases, and has access to contextual information that enhances its capabilities. And lastly, the digital twin also separates concerns of its associated IoT device. So if different IoT devices are introduced, the architectural component changes are isolated. So the future work that I will do on this architecture is that I will evaluate the provisioning process of the heterogeneous IoT devices further, and then also test the management and rule-based monitoring of the heterogeneous IoT devices. Thereafter, I will test the machine learning-based monitoring of the heterogeneous IoT devices with integration of different types of data sources, and then also manage the deployment of models and services associated with the digital twin across a fog network of IoT devices. Thank you.